Happy with the coffee break? Coffee? Caffeinated? Awake? Not hungry anymore? So because you are still going to learn for a couple hours and before you can get dinner. Okay, so let's get started. So last lecture, I introduced to you how we know that dark matter exists, and we showed all the evidences, and we talk about what type of properties dark matter has to have. Today we'll get into more models, where we'll see first the WIMP dark matter model, and if we have time, towards the end, we'll also start on the Axion. So, but to start the lecture, I think we should start with a couple questions. And these would be the questions that you will ask yourself or ask someone who tells you about their favorite dark matter model. And the 4 questions are basically what I listed here. And more often than not, when someone tells you about dark matter model and you start with these 4 questions, at some point they will fail to answer your question, and then you know their dark matter model is not great. Okay? So the first question you ask them is, do you have a Lagrangian? If you don't have a Lagrangian, you cannot write down an interaction, then you are just blah, 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 this is my dark matter model, right? The second thing that you ask people is, how is it produced in the early universe, right? As we know, dark matter was around at the time of the CMB and even much before that. So if they cannot tell you how it is produced in the early universe, then they don't have a dark matter model. And we'll be looking at this a lot in today's lecture, the second question. The third question you ask them is, is your dark matter well motivated? And does the particle you want to introduce solve some other problems? And if you want to answer yes for these questions, then basically it left with you with 2 dark matter candidates. The first one is the WIMP, weakly interacting massive particle, which we'll be talking about today. And the second one is QCD Axion, and we'll talk a little bit more also in the next lecture. So the last question you ask them is how to look for it. And a very similar cousin to this question is, have you already seen it, right? If they say yes, it means it's not dark matter, probably. And if they say no, then maybe the dark matter candidate is already excluded. Okay, so I'm not sure how awake you are, so let's start with a game, okay? So let's say you have a drunk uncle. I guess everybody has one, right? He come to you and he was like, my favorite dark matter, I think, dark matter is coronavirus, right? Okay, so does he have a Lagrangian? No, right? Okay, good. -1 point. How is it produced? Is it produced in the early universe? Probably not, because early universe is very hot, and coronavirus doesn't sustain in high temperatures, right? Is it well motivated? Probably not. We'd better not have it, right? Okay. Have we seen it? Okay, so this answer is yes, right? But you don't want this answer to be yes, because it's not dark matter if we have seen it. Now we know how much there are, and it certainly is not dark matter. Okay? So that's basically the 4 questions you ask yourself when people tell you about a dark matter candidate. Things like primordial black holes fail at this stage. There are many dark matter models failed at this stage. Most of them fail at this stage, but we still look for them sometimes. If they are byproducts we can look for when we look for more well-motivated candidates. So the last lecture, I will mainly be telling you about the 4th question. Today, it will be mostly 2 and 3. Okay? And the examples we'll be using is WIMP and Axion. Okay? So, so maybe to be more specific, QCD Axion. So, now everybody is awake? Okay. So at the end of last lecture, I told people to take a look at the FRW universe. I hope everybody did it, so because I'm going to go through this very quickly. So if we have an early universe, which is radiation dominated, then the energy density, which is a dimension 4 object in my unit, scales as temperature to the 4, because the temperature is the only scale, like in the early universe, hot early universe, so that has to be the scaling. Rho equals temperature to the 4. Remember, temperature is the energy unit, right? So we can compute from this FRW metric the Hubble scale to be equal to T squared over M Planck. Okay, people familiar with this? The third thing is that as the universe expands, so A is becoming bigger as time goes on, so like the universe expanding, as the universe expands, the radiation energy density will go down as 1 over a to the 4. So like if the universe expands by a factor of 2, then, well, like if a changed by a factor of 2, then like the energy density changed by a factor of 1 over 16. So this is for radiation energy density. And it is basically coming from the fact that like its energy goes as T to the 4. The radiation number density, so photon number density, goes as T cubed, because the average energy of a photon when the temperature is T is equal to T. So number density of radiation goes as 1 over a cubed, right? Because it scales at T cubed. And the number density of matter and the density of matter, energy density of matter, both goes as 1 over a cubed, right? So compared to radiation energy density, the matter redshift much slower, and the radiation redshift much more. So the last relation requires a little bit more mass if you are playing with this metric. And what you are going to find is that the Hubble scale is directly related with the age of the universe, roughly going as 1 over 2 times t. So as time goes on, Hubble gets smaller and smaller. Okay? So what we are getting out of this picture is basically the following. As my time goes on, increases, here like I'm doing a log-log plot for, so the temperature, the energy density of radiation, matter, everything is going down as a function of time. And the other thing is like the Hubble is going down as a function of time. Any questions about this? Okay, no? Good. So if you, because like if you do, like you should speak up now, because we are going to use some of these results, like again, like when we work out the different dark matter evolutions in the early universe.
Sorry, how did you scale the axis? Is it log rho t?
Oh, no, like log rho, log t, log Hubble, everything. It's just like schematically telling you that as time goes on, like the density is going down. Right? Okay. Okay. So for radiation, this is always true, and for matter, we'll see how it actually does in the early universe. Okay. So oops. So that's the FRW universe. Now let's actually look at a dark matter candidate. And we will, today we'll start with WIMPs, and we will slowly build up a model of WIMP. Okay, so we'll go from the simplest Lagrangian you can write down and see how eventually we get to what is known as the weakly interacting massive particles. So as we said yesterday, right, there are ways where particles doesn't decay, right? Either they are light and weakly coupled, or there is a symmetry. So the WIMP belongs to the case where there is a symmetry that is protecting it from decaying, like the electron, like the proton, and maybe also the neutrinos. So in the case of the WIMP, let's start with a particle which carries U1 quantum number. Let me just call it U1 dark matter. which basically says like there is a conserved dark matter number. The dark matter, there can be like a dark matter particle and an antiparticle. They can annihilate, but this number cannot change if I'm looking at a single particle. So like, which means that a dark matter particle cannot just propagate and decay away. Like it has to find an antiparticle to annihilate with if it wants to be gone. Okay? So, and then I can write some sort of Lagrangian, and let me call my dark matter psi. So it's a fermion. And let me just write down the simplest thing possible, right? That I describe a fermion which doesn't interact, actually, which basically I have a kinetic term for the fermion. And then like the fermion gets a mass, which is equal to m psi. So this is going to be the dark matter mass. Okay, so with this Lagrangian, there is a conserved fermion number, psi number, which makes sure that the dark matter doesn't decay. Okay.
What is D cross?
Actually, like I can just write a partial cross if you want. So like this D slash is so this is basically the Dirac Lagrangian, and this is defined as a gamma mu partial mu, right? Like if you learn field theory, like you are going to learn this, but like all what we care about for this class is that this is a kinetic term. It just says like the particle has kinetic energy. Okay, so you don't need to worry about this. Okay, the important thing is this term. It has a mass, and what this piece ensures is that this particle has a normal dispersion relation of a relativistic particle. So the energy is equal. Energy squared is equal to momentum squared plus mass squared.
Yeah, it's because I think in field theory, D need psi bar, D need psi, not the psi bar, D need psi.
Huh? Sorry. What?
I think in field theory, we write the kinetic term as D need psi bar, D need psi.
Yeah, so like that's for scalars, right? Like, so if you have a Klein-Gordon field or you have a non-relativistic field, yeah, then you do d mu psi, d mu psi. So this is a fermion, so it satisfies the Dirac equation instead of the Klein-Gordon one. So anyway, but like it's not very important. Don't worry about it. Okay. So the one thing that you can read out of this Lagrangian, so any Lagrangian density is dimension 4. So and the mass, energy, right, as I said, is dimension 1, which means that the fermion carries dimension 3/2, which we'll use a little bit. Okay. So what we have up to now is a massive, stable particle, right? So if I only have this particle, it cannot be produced. There's nothing, if it doesn't interact with anything, it's not going to be produced in the early universe. So certainly it's not actually a dark matter candidate yet. So in order for it to be a possible dark matter candidate, we need to couple it to the standard model, right? So in addition to this Lagrangian, I will add an interaction term, which is the simplest one can add. And actually, like, you shouldn't really worry about the gamma matrix contraction. It's a dimension 6 operator, which couples 2 of the dark matter fermions with 2 standard model fermions. Okay. So as I said, fermion has dimension 3/2, so this has dimension 6. So and Lagrangian density has dimension 4, so it goes as 1 over lambda squared, where you can think of this lambda as some high energy scale. So this interaction, famously, is a 4 fermion interaction. It is first written down by Fermi, and it describes how fermions scatter with each other. If I draw a Feynman diagram, this is what it is. Okay, so so if time goes this way, then what it describes is I have 2 fermions. They annihilate into 2 standard model fermions, right? So I can have time go this way. Then what happens is I have some 2 standard model fermions, and turn into 2 dark matter fermions, right? Okay. So I can also go this way in time. Now what happens is I have some dark matter particle coming in, scatter with the standard model fermion, and become a dark matter fermion and a standard model fermion, right? So that describes a scattering process if time is running this way. So all of these processes come from this Lagrangian term. But we are not going to go into details, computing Feynman diagrams. Everything we are going to do is a dimension analysis, and we track like the behavior of the system as time goes on. Okay. Any questions about this? Lagrangians? Okay. Yeah, if you have never seen things like that, we can also chat afterwards. You can ask me questions. Okay. So, this is seen as a cutoff scale for this for Fermion interaction. So in the standard model, actually also happens, and it describes. So this interaction, for example, describes how neutrons, protons, and electrons and neutrinos interact with each other. And usually, such a suppression comes from integrating out a heavy particle in the middle. Which can be, for example, a W boson or D boson, right? So at high energies, right, if I go to really, really high energy, temperature that is even much, much bigger than lambda, then certainly I don't really care if this particle is massive or massless. Every particle looks like it's massless. And the cross-section that I'm going to get from such an interaction has to go depend on only the temperature, because that's the only energy scale in the problem. So in this limit, this is all I can get, because the cross-section is dimension length squared, and the temperature is dimension 1 over length. So this is basically the only thing that you can write down at very, very high energies, right? So when temperature goes below this lambda scale, right, then the interaction is a little bit different. So now the interaction has to be proportional to this 1 over the suppression scale squared. So in this case, the cross-section will go as temperature squared over lambda to the 4 for temperature that's, let's say, below the scale lambda, but it's still larger or comparable to the fermion mass. So these are going to be the only cross-sections that we'll use for this lecture. If you don't know about cross-sections, all you need to remember are these two, and then that's it. Okay?
The lambda interaction would be caused by electromagnetic or weak interaction?
So here, let's forget about all standard model interactions. This is the only interaction term I have. And in the end, I'm going to tell you what this particle is going to be for WIMPs. But for now, it's just something, okay? I don't care what it is. It has a mass, and it's a mediate interaction, which is short range, and that's why you get a cross-section like that. Okay? All right, let's accept these two cross-sections, and then let's see what does it tell us as the universe evolve. Okay, so the first thing that we want to establish is, as I said, last lecture, WIMP is a thermal dark matter candidate, meaning that at very early universe, it is thermalized with the standard model. And let's see it is actually the case, right? So in order to say, I have a particle which is thermalized with the standard model, then what it is basically saying is the interaction rate, or the rate of dark matter going to standard model and a standard model going to dark matter is fast enough such that this process is balanced, right, in equilibrium. And the way to compute the rate for a particle, psi, to go into a fermion, a standard model fermion is basically so let's say I have a psi which is going into a bunch of psis. Right? So the rate of this process going on is going to be equal to the number density of the psi particles, right? That's how many you can scatter with, times the cross-section, which is how likely you are going to scatter with each one of them. So as you can see that this is a rate, right, which is the time, which is energy, 1 over time, which is energy. This is the energy cubed, 1 over energy squared, so that has the right unit. And as I said, in the early universe, if I radiation dominated, then every particle has to have an energy density, which is T to the 4, and the number density T cubed. So basically, this is very simple. When T is bigger than lambda, what I have, gamma is equal to T cubed times 1 over T squared. So it's basically T, right? And at later time, when T is a little bit smaller than lambda, then basically what I have is going to be T to the 5 over lambda to the 4, right? So that's the rate, right? It's an inverse time scale. Now I have to compare with the time scale so that to see like if this rate is fast or not, right? And the time scale that I need to compare with is basically here, right? So the universe has some lifetime, which is T, which is equal to 1 over Hubble, right? So if like this particle is propagating in the universe, and every Hubble time it can find something to annihilate, then or interact with, then it is roughly in some equilibrium. If even like within a Hubble time, as the universe already expanded, it cannot find something to annihilate with, then there's no equilibrium. So the criteria for whether this particle is in similar equilibrium or not is basically the rate of interaction over the Hubble rate, which it is equal to m Planck over T for T large, and some maybe let's see, m Planck T cubed over lambda to the 4 when T is a little bit less than lambda. Either way, what you can see is that because m Planck is such a large energy scale, at early time, the WIMP particle is always thermalized. So this rate, this ratio is always much bigger than 1, right? No matter in this case, or in this case when like a T is order lambda, right? As long as lambda is not some like a crazy scale, there was always like early enough time that the WIMP was thermalized with the standard model. So at this time, basically what we have is that I have rho gamma. Let's use another color to say rho dark matter. Okay. So the photon number density is pretty much always going like this as a function of time. So what this tells you is at some early time, this is what it has to do, right? Because they are thermalized with each other, so they have roughly the same energy density. Okay. So now we know this line doesn't continue all the way, right? We do not have the same amount of dark matter as photon today, so it has to change. So and the things change when you cross a threshold, right? So what is the threshold here? Anyone? Huh? Lambda, that's one guess. What is the other possibility? There's a math scale here, also in the problem. I have written it down actually and highlighted it. What is it? The mass, right? Okay. So the behavior changes when the temperature is equal to the mass of the particle. Okay. So what happens now is that this equilibrium between things going this way and this way is no longer in equilibrium. Okay. And let's see how it works. So for all practical purposes, I will assume all standard model particles are massless. for this exercise. So all of them is going to get some Boltzmann-ish distribution, right? So this is the number density of a Stern model as a function of energy, right? And the peak is when energy is equal to temperature. Okay? The dark matter particle, at the time when temperature is comparable to its mass, becomes non-relativistic, right? So it becomes, it started being from radiation and it started becoming matter-like. So when some particle becomes matter, it will also redshift, but the total energy doesn't change very much anymore because most of its energy is the mass energy instead of kinetic energy, right? So the dark matter I want to produce would have a mass or energy, which is here, while the standard model fermion or photon bath is decreasing in temperature, right? The temperature is continues to go down. So in order for a standard model particle to find another standard model particle to produce a dark matter, like two dark matter particles on resonance, right? You cannot do it anymore unless you are in the exponential tail of the Boltzmann distribution, right? Okay. So so basically, now this rate gets very suppressed. The dark matter is still annihilating, but there's no particle that is coming back, right? So quickly, what you'll expect is that the dark matter particle, or like the energy distribution, is not going to be the whole like white region here, right? It's going to be only like those which has energy much more bigger than m. So the amount of dark matter particle will become exponentially suppressed compared to the amount of standard model particle, and the suppression should go as e to the minus m over t, right? With me? Yes? Okay. Hopefully yes. So this is going to be what happens, right? Like it's exponentially decaying now, like decaying really, really fast as a function of time. Okay? So does it go all the way? Also not, right? It cannot. If it continues to go all the way, like now we have no dark matter, right? So at some point, like this process also has to stop, right? When does it stop? And why does it stop? You want to talk to your neighbor? Maybe not, okay. If you don't want to talk to me, your neighbor very much, then I can tell you, okay? So, so what happens is now like I have very much, like I don't have like a lot of dark matter anymore, right? Because they get exponentially suppressed. So this amount of dark matter density that I can interact with is no longer T cubed, right? So basically, what happens is at some point I need to re-examine like this relation here, right? Because the interaction rate, the cross section doesn't change, right? But the interaction rate starts to change because there are not that many particles to interact with. Okay? So let's say this amount of particle that I have to interact with at this temperature is called n stop, right? By the time like I stop to interact, and I will want to know like what is this density n stop, right? So what is this point? So the condition that I'm going to use is again still like gamma over h, so it's equal to n stop times the cross section, right? Let me just say like a temperature is still order lambda, so I have 1 over lambda squared, right? This is cross section, and temperature is still order lambda, so Hubble scale is lambda squared over n Planck, right? And the interaction stops when this is roughly equal to 1, right? And what this tells me is n stop is equal to lambda to the 4 over m Planck. Or let me write it this way. Okay? So what it tells you is that it does get very exponentially suppressed. It gets suppressed by a lot. If it is a thermal density, it will be order lambda cubed, right? Like all the mass scales, lambda, m, like I'm assuming them to be all comparable. Now it is suppressed by a big ratio, a very small ratio of like a lambda over m Planck. The Planck mass is some like a really large mass, so it's a very small amount compared to the original density to start with. But at this time, this quick annihilation of the dark matter particle stops, and that's when we say that the process has freeze out. Okay? Meaning that the number density of the dark matter particle is only diluting, it's not changing anymore if we count the total amount of dark matter in the universe. Okay? Good. All right. So after it is frozen out, it will redshift, right? So it will start to redshift, and as I have here, it is now matter, right? This particle is now matter. It's not radiation anymore. So the number density and energy density both go as 1 over a cubed. Here, this line is going as 1 over a to the 4 because it's radiation, right? So this one is radiation, so it's 1 over a to the 4. This will redshift much slower, so the dark matter density slowly get to be closer to the radiation density again, right? And naively, I would say, like maybe at some point it cross again, and this point is called matter-radiation equality. And from the CMB, we can measure like what this point is. It happens roughly when the universe temperature, well, like when the photon temperature is order 0.1 eV. Okay. So, so as you can see, the dark matter is thermalized. It goes out of equilibrium for a while. And then like it redshifts a little bit slower than the radiation. At some point, it catch up with the energy density of the radiation at the time when the temperature is order 0.1 eV, right? So in this process, let's say if I say the lambda and the fermion mass is roughly the same scale, then I have one scale in the problem, which is lambda, right? I need to do this complicated maneuver, right, to first I'll go out of equilibrium and then like get back to be the same density, right? If my particle wants to do all of that, it probably tells me that there is a unique lambda scale which allows this particle to do it, right? So now let's find out what this scale is. So the next question is, what is lambda? That gives me dark matter. Okay, so actually we are almost there. We said we have found already what is n-stop, and we know that after the time n-stop, it starts to redshift like matter, right? And the other thing that redshifts like matter is the number density of radiation, right? So what it means is after this point, the number density of dark matter over the number density of photon doesn't change anymore, right? Both of them scale as 1 over a cubed, so the ratio is a constant over time, right? So at early time, this one is n-stop, and at early time, this one is lambda cubed, so this ratio is roughly lambda over m Planck, and it stays this way throughout. So the matter radiation equality is not about like the number density being the same, right? We don't know what's the mass of the dark matter. what the CMB measures is the energy density of the dark matter being equal to the energy density of radiation, right? So now I need to do an additional step. If I do rho dark matter over rho gamma at T equals T equality, which is 0.1 eV, what I'm going to get is lambda times the mass of the particle, which I'm taken to be order lambda, also order lambda, over 0.1 eV times m Planck, and this has to be equal to 1, right? Now I know what this is. This is 10 to the 18 or 10 to the 19 GeV. This is 0.1 eV, so I can solve for what is lambda. And if you do it, you're going to find that lambda is all for order 10 TeV. Okay? Everyone following what's going on? Okay. So, so this scale is interesting, right? Because as we know, it is the scale that is very close to the Electroweak scale, in the center model. The weak gauge boson has like a mass of order 100 GeV. The Higgs is order 100 GeV. And the LHC was built to look for physics around the 10 TeV-ish, right? It is a scale that is accessible to us, experimentally, and in principle, we can build experiments already now to look for the existence of particles with the interaction with mass that is order TeV, and also like with the interactions that are suppressed by TeV. Right? So it's interesting. Oh my God, sorry. Maybe too interesting. Okay. So of course, like through all of these derivations are very sloppy, right? But I say like I already told you last time, because I told you like 3 equal to pi equal to 1. So there are a lot of things that like order 1 numbers that I didn't include. So there's one thing called G star, which basically says like it parameterizes how many degree of freedom are there in the standard model. So this line is not a straight line. It has bumps, because like a standard model, there are also particles which are freezing out. So it actually goes a little bit like this. So the temperature of photon like actually have some like increases when some particles freeze out in the early universe. So there are other things. For example, like the interaction is not really 1 over m fermion. It has 4 pi's. It has coupling constants. And if we do it more carefully, this number actually becomes smaller. So if we assume that lambda, 1 over lambda squared, is actually, I'm using actually the Electroweak interaction, G Fermi, right? And I'm assuming, let's say, like I put in all the order 1 numbers that I want, then eventually, like the scale for this particle that I'm getting is going to be from around 1 TeV to 10 TeV. Okay, and right now, like actually, like many of the WIMP candidates are already excluded. There is still one that is very well motivated, and is known as the Higgsino, which will have a mass of 1.3 TeV, and that's a particle that we are still targeting with direct detection experiments. And for most people, it's the only surviving WIMPs in the spectrum, but like it is actually the most well-motivated, just like it couples very weakly, and it is hard to look for it with the experiments. Okay, so that's basically the thermal history of WIMPs, and this is roughly the mass scale that we are targeting if we really think dark matter is some particle which interacts with us through the weak interaction. Any question about this part? Okay. So what do we do like with all of these computation, right? We answer this question. For WIMP, This is how it is produced. It was thermal to begin with. It forced out thermal equilibrium and eventually like catastrophic density, right? So now I need to answer this question, like how is it motivated? Okay. So WIMP is actually the like if you ask most particle physicists, it is the most well-motivated dark matter candidate. First, because of the energy scale that it has and how we can look for it. But also, more importantly, it is related to a lot of theories which are written to address what is known as the electroweak hierarchy problem. Have people heard about this? Yes? No? Some of you. Okay. So the electroweak hierarchy problem is the question, why is the Higgs mass so light? Okay? Or why is the W boson especially so light? So in the particle physics, in the standard model of particle physics, we have all these fermions, which are protected by chiral symmetry, so that's why they are light. We have gauge bosons, which are protected by gauge symmetry, which are why they are light. But there's one scalar particle, which is the one that you probably heard about, the Higgs particle, which is a scalar. So, usually people write the Higgs Lagrangian as something like this. And there's no symmetry that is protecting the Higgs from being from getting quantum corrections to its mass and become ultra heavy. Especially, what we found is you can do a loop of top quark. Okay, so the exactly diagrams doesn't really matter, but this loop diagram is going to contribute to the mass of the Higgs boson and make it heavier and heavier. And depending on the cutoff of your theory, what you will find is it tends to make the Higgs mass squared equal to whatever the cutoff of your theory is. And for particle physics, the cutoff is usually considered to be the Planck scale. And what this analysis will be telling you is that I would expect my Higgs mass to be, or the vacuum expectation value of the Higgs especially, to be order n Planck. And that is certainly not what we're seeing, right? The Higgs mass that we know is 125 GeV, while the m Planck is 6 times 10 to the 18 GeV. So in Planck unit, the Higgs mass is 10 to the minus 16. And this huge difference in the two fundamental scales in the standard model is what is considered the electroweak hierarchy problem. And people have built many models to explain why the Higgs particle is so light. Okay? So last time I told you about the cosmological constant problem a little bit, which is something in Planck unit being 10 to the minus 120. So this is not as bad. It's only 10 to the minus 16. Or usually people say it's squared. So you actually have 10 to the minus 32. But they are both tiny, tiny numbers that we don't know the origin of. And we generally expect from QFT to be order 1. Okay? So that's a problem. And people have built models to try to explain this problem. And these explanations usually involves introducing new particles at the electroweak scale, at the scale of G Fermi, a couple hundred GeV or TeV, to cancel this divergence coming from the top quark. And this mechanism introduce new particles at this scale. And many of these particles, especially the lightest one of these particles, would be a natural dark matter candidate because it is protected by some additional U1 symmetry, which is conserved in these models. So that's basically the story of the WIMPs. We see that these particles, which are called WIMPs, who are dark matter candidates, naturally arises in a UV theory, which is written to explain why the Higgs is light. And for that reason, people like it a lot, because it's well motivated from something else, right? Not like just to have dark matter in our universe. And that is also the reason why we build like tons and tons of xenon detectors to look for the existence of these weakly interacting massive particles. And in the last lecture, I'll be telling you something about these experiments. But that's it all for the WIMPs. Any questions?
There is a question.
Yes.
What about the interactions between dark matter and fermions? Is it possible to this number be verifiable on the lab?
Yeah, that's what I'm going to tell you when we go to experiments next time. Like, yes, we will be able to look for it. And it's exactly that interaction, which is producing these dark matter particles. That is the interaction that we are looking for with these experiments. So for the production, or like the freeze out, we are basically interested in this process, right? When we talk about detection, well, we are interested in this process, where a dark matter particle come in, hit your detector, leave some kinetic energy behind in your detector, and you try to look for it.
What is this type? Is it possible to do an experiment that seeks this in a short period of time?
So we actually as I'm saying, initially there's a lot of possible WIMPs. Right now, after 20-ish years of work, we are left with one, which for very complicated reasons is very hard to look for. And but we are trying, and maybe at some point we'll get there. But it takes time. Okay? Yeah.
Why is missing the kinetic term in the Higgs field?
Yeah. So there are also the kinetic term, and then there are all kinds of interaction of the Higgs. Here, I'm just writing down the potential mostly. Yeah, we should think of it as this. Okay, right. Okay. If no more questions, we'll move on to Axions. Yeah.
This study would be what the community calls the dark photon, or not?
Psi?
Yes, this dark matter particle.
So the psi is the WIMP.
Yes, okay.
Right. So dark photon is something else. Actually, I won't be covering dark photon in this lecture. But yeah, we can play with dark photon too. No, actually, I will towards the end. But yeah.
You mentioned that the model has the U1 symmetry, but is it global symmetry or a local symmetry?
It's a global symmetry. If you do supergravity, then I think maybe it can also still be a global symmetry. But it doesn't really matter. No matter it's a gauge symmetry or global symmetry, it's conserved. Okay. All right. So that's WIMPs, and you can probably find a much more precise version of this thermal history in a lot of lecture notes, which probably requires a little bit more QFT than what I'm using here, but it is standard material. So now I will be telling you a little bit more about Axions, which is another dark matter candidate. So I'll erase this part. Here. And maybe I will come back to this part. Okay? So, Axions. And especially QCD axions, but the QCD axion is a little bit more complicated. So for the thermal history, I will just do a generic axion. So for the axions, I will do, actually, like, when do I start? Did I start?
I think at 20, so you have almost half an hour. It's 12,
Okay, okay. Okay, yeah, that's good. Thanks. Okay, so so now, like, let's go to axions. So for the WIMPs, as you can see, I did something called a bottom-up approach. I started with a very simple Lagrangian, right, and I slowly build meanings to it. And eventually, I told you a little bit about the Electroweak hierarchy problem. So I start with some very phenomenological considerations and eventually go to a real model, right? So for axion, I want to do the opposite. I will do top-down, which means I will first tell you like what type of problems does the axion solve. And to do that, I will first need to tell you about what is known as the strong CP problem. How many people heard about this? Oh, OK. So more people knows about axions than WIMPs. Time has changed. OK. So how many people know P and C and P? Does it mean something to you? OK. So P, not everybody knows, I will tell you. P is parity. OK? So parity is basically I have a left hand, I have a right hand, and they are mirror images of each other, right? And that's basically parity. So and CP, in like all quantum field theories, like CPT is conserved, so it's basically equal to T, and this is called time reversal. Okay. Meaning if I'm going forward in time or backward in time, I change the like a T, it's a T going to minus T thing, and here it's like X going to minus X, right? So the object we are going to examine with these discrete symmetries is a neutron, okay? So a neutron is a particle which can have a magnetic moment. Well, it's neutral, so like there's no monopole moment, but like it can have a magnetic dipole moment, it can have an electric dipole moment, in principle, right? So what happens if I apply a P? How does, first, like, how does D change? Stay the same or opposite? Huh? So D, right, is basically the charge times the length, right? So the length changes sign, so D changes sign, right? So D will go to minus D, right? How does mu change? What is mu? Mu is the angular momentum, right, roughly. So it's a length scale times the velocity, right? So there are two lengths, so it doesn't change, right? If I do x minus x, and I change both of them, so it doesn't change, right? So mu stay the same, right? Okay. So what you see is if I do a parity operation, then mu dot d goes to minus mu dot d, right? What about time reversal? How does the mu change? Does mu change? Okay, it goes to opposite, right? And well, what about D? There's no time, right? So D stays the same, right? So the same, if I do a time reversal, right? Mu dot D goes to minus mu dot D, right? So if I take a measurement in the lab of the neutron and measure like a mu dot D, right? If I get a non-zero number, it means both parity and the CP is violated, right? If non-zero, then parity is violated and CP is violated. Okay? So maybe like you will say, like, why is it violated? Like, do we expect it to be violated? Well, the Electroweak interaction does violate both. And the parity violation of the Electroweak interaction was discovered by, well, like theoretically by CNYang and TD Lee, and then experimentally verified, well, I would say like experimentally discovered by like Madam Wu with what is known as the Cobalt 60 experiment, where she measured like the cobalt decay and realized that parity is violated in the weaker interaction. So CP is also violated by the weaker interaction, and the measurement that people did is KK bar mixing, but like the CP violating angle of the weaker interaction enters the Kabibo-Kobayashi-Masukawa matrix, which is the matrix almost all flavor physicists study. And in this matrix, there is a phase which is called delta CP, and you can find it to be order 1, okay, like in radians. So what we know from the weak interaction, electroweak interaction, is that both parity and the CP is violated at the order 1 level. Okay, so so you say like, okay, so maybe we should measure electric dipole moment or like a mu dot d for a neutron because, I mean, electroweak interaction violates these discrete symmetries, so probably strong interaction does it too. Okay, so that's the expectation, and people think strong interaction violates CP, right? So the theorists go to experimentalists, can you measure this? And experimentalists did it. And more often than not, we found an answer that we don't want. And what they discovered is that the electric dipole moment of the neutron in the direction of the magnetic moment has to be smaller than 10 to the, well, first thing, like we know like neutrons have magnetic dipole moment, and that is something that is known like for a very long time. So basically, like that's why like the constraint is really just on the electric dipole moment. And what we found is that this electric dipole moment of the neutron has to be smaller than 10 to the minus 26 e centimeter. Well, okay, so as actually like many people asked like yesterday, when I say like some dark matter doesn't interact with us, I'm not saying like it doesn't interact with us at all, right? So like there's no way you can measure 0. Like all you can say like is something is less than like it's very 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 tiny. Like experimentally, there's no way you can measure 0. Here it's also the case. You can never measure 0. But you can say like the electric dipole moment is really, really tiny. And this really looks like a tiny number. How tiny? Well, let's see what we expect, right? So theorists say that this number is equal to basically theta QCD, which is a phase, okay, like the delta CP phase, multiplied by E times the Fermi, right? And the Fermi is roughly like 10 to the minus 13 centimeter-ish. And combining these two tells me that the theta QCD, well, if I do it more precisely, is now like smaller than 10 to the minus 11-ish. Okay? So now there is a puzzle, right? The weaker interaction clearly violates the like a CP. And this angle is order 1. An angle that is very similar in origin, the theta QCD, is less than 10 to the minus 11. Right? There's so experimentalists are always right, right? So something weird is happening to our theory. Okay. So the question that we will need to address theoretically is why is the theta QCD so small? And So in next lecture, I will be telling you about what is known as the QCD axion, which is a concept, or like a particle which is introduced to explain the smallness of theta QCD. But more importantly, we'll show like how, like with some pictorial way, like what it actually what it actually doing to relax the electric dipole moment of the neutron. And then we'll say like how this particle, which is introduced to explain why theta QCD is so small, can also be the dark matter in our universe. So that will be next lecture. So since we have still some time left, let's play another game, okay? So in the first lecture, I told you guys that every lecture I'm going to let you do dimension analysis so that you know the unit system, right? So now let's do it, okay? So here's the problem. Question, okay? Let's say we are conquered by aliens, and they come to Earth, and they come with this as their scale, okay? So it's an absolute scale, which is made from material that we don't know, has nothing to do with the Higgs, gets its mass, measures everything a scale would measure, but doesn't respond to any change of our fundamental constants, okay? So I have a scale from, actually, is it the way like I should write it? Which measures what a scale like you have in your bathroom like measures. So now the alien took Pedro and put him on the scale, okay? And of course, like the scale is put on Earth, right? So now what happens? Now the alien says, let's see what happens if I change the Higgs Electroweak Higgs wave, or like the Higgs mass, or like any quark masses as a result, and I reduce it by a factor of 2, let's say. So all of this number becomes this number over 2, okay? What happened? What happened to Pedro? Any guesses? Like so I don't know how much you weigh, but let's say some number. Huh? It's a secret, okay. Let's say like I have a number to start with, right? How does this number change? You want to talk to your neighbor? Okay. Anyone want to guess? No? Nobody? Wow, you ask many questions. What do you say? What's your name? Elliot.
I would say that nothing happens.
Nothing happens. Why do you say that?
Because you define the scale in terms of the natural constants, and if all natural constants change.
Oh, no, like my scale is going to tell me a number in Newton. Okay?
What units are on the little box?
Huh?
What units are in the little box you drew?
No, it's a number. Like Pedro won't tell me, but like it's a number. Huh? Oh, like all of these, like the electroweak valve, the Higgs mass, the quark masses, and the electron mass. Okay, all of them become a factor of 2 smaller, right? Other guesses?
Half by 2.
Huh?
Half by 2.
Up by 2.
You have the mass will reduce by a factor of 2.
The mass will, well?
Is it 4 bigger?
Huh?
It's 4 times bigger?
It's 4 times bigger. Why? So first, like, you say, like, let me address him first, okay? So you say, like, the weight, the number you measure is going to be the number over 2, right? Okay? So, and the reason you say is because the electron and the quark masses become half of that. But, like, we are mostly made of protons and neutrons. And the protons and neutrons doesn't really respond to the Higgs valve, right? So the proton mass mostly come from confinement. It's always 1 GeV. Even if I change the like a quark masses a little bit, it won't change the mass of the proton very much. And electron is a very small amount of energy density. So this is not true, but good guess. Okay. So too bad, Pedro is not getting like lighter. Very a lot, okay. Like you said, like a factor 4, okay? So you say, so guess 1, guess 2, like this becomes 4 times this, right? Why do you say that?
Because when we measure the force is in 1 over time as squared.
Okay.
So we had 1 over 2, so we had 4 times because it's 2 plus 2.
So why is R becoming a factor of 2 bigger?
Yeah.
Why is that?
2 over 2.
So you say like it's because R goes to 2 times R? Why is that?
No, over 2.
R becomes R over 2?
Yeah, so like the force is proportional to 1 over second to a square, to over 2.
1 over. Ah, okay. So you say like it's meter over second squared.
Yeah, only because the Neutron and mass is concept because are the same. So
Okay. So you're getting somewhere, okay? But like you need to tell me like how does things change to make it a factor of 4 different? A little bit more. So what is the biggest thing that has happened to Pedro, like when something like this happened? So what is the fundamental constant, or like what is the object like that changed when I changed the electron mass? How does the atom change? Does the atom change if I change the electron mass? How does it change? Huh? Somebody says size. Can you be more specific? Okay. Why does it get bigger? Good. So the Bohr radius is 1 over alpha ME, right? So my ME becomes a factor of 2 smaller. So my Bohr radius gets a factor of 2 bigger, right? We are made of atoms. And so what happened to us? We get a factor of 2, well, a factor of 8 bigger, right? Too bad. Yeah. R goes to R, okay? So now what else becomes a factor of 2 bigger in size? Or 8? Which volume? All volumes, right? Like the Earth gets a factor of 8 bigger, right? So now instead of this picture, the Earth is this big, right? And let's say like Pedro is a point, like on Earth, right? So what happens for the gravitational force? Right? Like it's 1 over r squared, right? So it gets smaller by a factor of 4. Okay. So F becomes F over 4, right? So so what you get is that the scale is going to like print a number which is a factor of 4 smaller. Okay, roughly. Apart from like the tiny changes to the weight, like the actual weight in kilogram, most of the effect is coming from the size of the scene changing, right? So this is how you see when I change the mass scale. Maybe the biggest effect you can get is not changing in mass, it's changing in the size, and that's how you get it gets reflected by the scale. Okay? Good, everyone? With that, I think I will stop and take questions. Questions?
Don't be shy. If there's anything you didn't understand correctly, ask it now.
No.
In all consideration, we only get in account the fermions. What happens if we include dark matter like bosons? What happens if we include dark matter like bosons? Bosons that dark matter.
So yeah, like so boson. I mean, like hydrogen atom is a boson, right? The number of hydrogen atoms in the universe is conserved. So they can still be conserved. But like, as I will get to like a little bit more, the axion is a boson, and there's no symmetry protecting it from decaying. So like in that case, you need like to have like a weak interaction, small mass to make sure that it doesn't decay. But yeah, like in terms of like symmetry, like you can have like boson with a symmetry or like a fermion with a symmetry that makes sure that it doesn't decay. Other questions?
Could you explain more about the coupling that you did on Lagrangian in the beginning?
The
factor
coupling?
Yes. When you were explaining about the Lagrangian and you did some lambda factor.
So you mean like a term like something like this?
Yes, yes.
So well, like so the real thing is actually much more complicated than this. You need to put in a bunch of gamma matrices. But like what this is like have a term, right? Like an interaction term which involves 2 dark matter particles and 2 standard model fermions, right? So when I have a bar, like if you want like in more like quantum mechanics, it's basically a dagger. It means like I'm creating a fermion, and this is I'm like killing a fermion, right? So here like I'm killing a fermion and producing a fermion, so like the fermion number is conserved. And here I'm killing a standard model fermion and creating one like that's conserved, okay? So in principle, like I have both of them in the initial state. Then I have a fermion and an anti-fermion. They annihilate and give me 2 dark matter particle, like vice versa, right? Or I can have a fermion coming in, scatter with another dark matter fermion, right? And then producing another fermion, standard model fermion and dark fermion, and that would be some process like this, right? So I have a going this way in time. Okay, so that's how you see that this interaction gives you dark matter standard model scattering, it gives you dark matter annihilation, and also standard model annihilation into dark matter. Okay? Cool.
There is an effective interaction Lagrangian, right?
Huh?
Is that an effective Lagrangian for the interaction of the winds, right? Of matter with wind.
Is it, what is the word?
Effective Lagrange.
An
Effective, yes,
Lagrangian.
it's an effective Lagrangian,
Okay.
yes.
Does the UV completion of that Lagrangian imply new particles?
Okay, so the question is like, is this like a particle, a new particle? Well, like for WIMPs, it's actually not. So this particle, like for WIMPs, is basically either the W boson in the Standard Model or the Z boson. So it's like an electroweak boson in the Standard Model. And especially, I think, like for dark matter scattering, it will be the Z boson. Okay, so it's just the Standard Model weak gauge boson. Like it's just coupled to a fermion, which is heavier than the Standard Model fermions. So this is honest to God weak interaction.
Okay, but are there any other models which complete the theory with other particles, like
Yeah,
fermions?
so, right, like you can introduce new particles to do WIMPs. You can do Z prime, right? I can have like another gauge boson which look like the Z boson, but like have a different mass, different coupling. So this is, and then like you can have dark photon. So you can have like, so this would be like a heavy particle, right? So heavier than the Z, and it will couple maybe like with a similar interaction strength as Z, or like you can have something more like a photon. So it's a very light particle, and with much weaker interaction strength. So those things can also be mediated interactions between like the Standard Model and the dark sector. So for example, this is called dark photon. Somebody was mentioning dark photon. That's what it is. And so there can be like all kinds of mediators people can come up with, which mediate interactions between us and the dark matter, right? So again, if we introduce these new particles, then we can basically like run this like a thermal history again. It will give you some sense of like what these particle masses are, giving a dark matter particle mass, right? So you can have like a like a higher dimensional parameter space for what can be the mass of the mediator, which is this particle, and what can be the mass of the dark matter, which is this particle. So, and then like you can change the coupling constant, all kinds of things like that. But if you do things like that, you are going to be able to answer very well the second question, right? You can say like, I change all of these parameters, it can still be produced in the early universe to be the right abundance. So second question is yes, but the third question, people will ask you, why do I need to introduce all of these particles when all I need is to introduce one dark matter particle, right? Then you will say, because I like dark photon. But that's not like a really good like a way to say like this model is motivated, right? So so that's why like, but like people are looking for this because they like well, like we can look for them first, and also like they are close cousins with the models that we're mostly interested in, and the detectors which will be designed to look for WIMPs will also be able to look for these things as well. So that's yeah, that's the story.
One last question. So in the model where electroweak gauge bosons are the mediators, in that model, is then possible to dark matter couplings to photons?
Yes. So the question is like, if I have some electroweak gauge boson as mediator, does it couple to photons? So actually, like in most models, it would. And there's actually like this arrow is also a detection channel, and it is called indirect detection. So we said that the dark matter frees out, meaning that the interaction, between dark matter happens at a time scale which is longer than Hubble time. But now we are very good at looking for things like X-ray, or gamma ray photons, right? We can even look for like annihilation of particles which happens at a rate that is much, much smaller than the Hubble rate, by just looking at the empty region and see if there are like random gamma rays popping up. So that's one thing that people do, and it's called indirect detection. And the process that people are looking at are basically dark matter particles through some mediator, maybe through like a loop of particles, and like giving you 2 photons. For example, like I can have things like this, annihilate through some loop into giving me 2 photons, things like that. It can be also big gauge bosons in the loop. The diagram can be even more complicated. It can, anyway, there are many, many ways like you can get photons and standard model charged particles from dark matter annihilation, for example, in the galaxy center or in dwarf galaxies. And those are the states processes that people also look for. And it also places constraint on several of the WIMP candidates, which is also contribute to us narrowing down the only candidate being the Higgs signal. More questions? Actually, like the leading, one of the things can be even be something like this, where like there is a charge state in the middle, then like you can have a photon like this. Okay.
More questions?
So dark matter could have a electric charge,
No, dark matter itself cannot have an electric charge.
but there's direct couplings with photons.
No, like, sorry, like here, like you need something else to turn like the dark matter into a charge, like charged like dark matter, and then like, it's, well, like it has to be some sort of loop diagram maybe. Exactly, like there are many, many different things you can draw, like which either turn the dark matter particle into a charged particle, or like it interacts with some charged standard model particle, which gives you a photon. But yeah, like you can get photons in many ways. Maybe I can draw you some more next time.
Okay, there are no more questions. Let's thank Junwu.